Hey everyone, welcome to Chem 1111. We are going to be looking at Chapter 2 for the next few lectures. And this is gas law. So this is more grade 11 chemistry, review, and expansion. See, I said expansion, right? Because gases expand. So that's a little joke. So we're going to start by looking at pressure. And there's lots of units associated with pressure. And these days, everyone seems to be under pressure, right? Look at the properties of gases, mixing of gases, stoichiometry involved with balanced equations, where gases are consumed and or produced. A little bit about the molecular view of gases and some additional gas properties such as density and how we can use gas laws to get identities, and a bit about the non-ideal real gases as opposed to ideal gases. Chemistry of the Earth's atmosphere, we don't really talk about that much. So we're going to use slides and our mini text to go through that. So we start with pressure, and we understand gas pressure, and there's various units associated with it. You have pressure because you have gas molecules hitting the sides. Now, this book, for some strange reason, uses lowercase p for pressure. I'm not going to follow that very often. I'll use uppercase P. Air around us is a huge reservoir of gas that exerts pressure on the Earth's surface, and that pressure can be measured with a barometer. So we have the pressure from the air around us pushing every which way, including onto a little circular disk of mercury, which then can go into an inverted tube, and you can create a barometer at sea level. 1 atmosphere pressure is used a lot, and I use atmosphere a lot, and I got to be careful about that because actually it's bar that is the SI unit for pressure, not atmosphere, but we use it a lot anyways. And units of millimeters of mercury are used because you can measure the height of the mercury in a barometer. We also have manometers. Again, this should remind you of grade 11, so you can have a gas in a bulb, and if the pressure of the gas in the bulb is greater than atmospheric pressure, then the arm, there's two arms in this U-tube, the pressure of the gas in the arm hooked up to the bulb, the level will be lower than the other end. This drawing here we're looking at is an open-end manometer, and therefore we can look at the difference between them and calculate the pressure of the gas. So it's the atmospheric pressure plus the difference in the height of the two levels. And conversely, if the pressure of the gas was less than atmospheric pressure, then the level of mercury would be higher in the arm closer to the bulb. Okay? So we have some units for pressure, and this is also on page 61, that 1 atmosphere is 760 millimeters of mercury. And it's also called 760 torr, capital T-O-R-R, short for this guy Evangelisto, I think his name is Torricelli, and T-O-R-R. And 1 bar is close to 1 atmosphere, right? An atmosphere is 760 millimeters of mercury, and a bar is 750.1 millimeters of mercury, or 750.1 torr. So a bar and an atmosphere are pretty close to each other. Technically, the SI unit for pressure is the Pascal, and 1 bar is 10 to the 5th pascals. We also use kilopascals a lot, and you'll hear that in weather reports, right? When they talk about barometric pressure, because if it changes a lot, that means that the weather is going to change, in theory. I won't bother with that. Let me go to the textbook here, and page 61, so I'm just scrolling down here. Okay, yeah, that's a silly question. So let's just jump straight to describing gases. And we have here that a gas will occupy the volume in which it's contained. So molecules in a gas move freely throughout the entire volume of a container, changing direction whenever they collide with other molecules or with a wall. Okay, so the molecules in a gas are relatively far apart compared to a liquid or solid. And so now let's look at some of these here and some of the gas laws. And we will look first at what's called Boyle's law. And Boyle's law is that volume is inversely proportional to pressure at constant temperature and amount. And for amount, I'm going to write lowercase n, where lowercase n stands for number of moles. Okay, so that is known as Boyle's law. Basically, if you squeeze something down to a smaller volume, then you've got to be exerting a greater pressure to make that happen. And Boyle did something what's called J-shaped tubes, not U-shaped tubes, but you see there letter J, and you see that you can increase the pressure and decrease the volume. The operational definition would be this: P1 V1 equals P2 V2. So that's the way I was taught it way back in 1923. So in one state, in one set of conditions, the product of pressure times volume is the same as the product of pressure times volume in another set of conditions. So when you have the inverse laws, you can write it like that. And then you can isolate for all sorts of things. Make sure that volumes are of the same units and pressures of the same units when you do something like that. So now there's other ones, but let me just make up an example of one. Let's say you had 3 atmospheres, and that was occupying 2 liters, and then we went to 12 atmospheres, so we want to solve for V2. Okay, so V2 is P1 V1 over P2. So 3 times 2 divided by 12, so half a liter. And some students like to not even plug in the equations. They just like to say, okay, the pressure quadrupled, so the volume has to be a fourth of what it was before. So a fourth of 2 is a half. And that's more hotshot kids who can do that. But if you can do that, kudos to you. Most of you are just going to plug in like you did in grade 11. And that's good. So that is the relationship known as Boyle's law, named after some guy, Robert Boyle. And so that's one. Now the second one is called Charles's law, and named after this guy, Jacques Alexander César Charles. He's a guy who hung out with the Montgolfier, who were the big into hot air ballooning in France. And apparently one time they were ballooning, and Charles's balloon went off course and landed in some field way on the outskirts. And some farmers who were working there on the outskirts of Paris had never seen such a balloon before, and they thought it was something from the devil when they took their pitchforks and ripped the balloon to shreds. And they don't say what happened to Charles, but anyways, an interesting story for sure. So Charles's law says volume is directly proportional to temperature. So the greater the temperature, the more volume the gas will occupy. And that temperature, I got to be careful here. Temperatures in units of Kelvin. Sometimes I'll try to trick you and give you the units in Celsius. You got to convert them to Kelvin by adding 273 and then take it from there. So that's a direct proportion. So we can then say that if volume is proportional to temperature, then volume over temperature is a constant. So the operational definition in 2 different sets of conditions is V1 over T1 equals V2 over T2. And that's at constant pressure and number of moles. At constant pressure and number of moles. So That is known as Charles's law. So let's just make up an equation here. Let's say that I had, I'll go to paint. There you go. Let's say I had 5 liters of some gas. Notice we don't care yet what the identity of the gas is. We're assuming all gases are ideal, and we'll get more to that very soon. And the temperature was 20 Kelvin. What would be the volume occupied by that gas if I doubled to 40 Kelvin? So you know it will be 10 liters. But if you want to use the equation, V1 over T1 equals V2 over T2. So V2 is V1 T2 over T1. So 5 times 40 over 20, which is 10 liters. So double the temperature. There you go, 10 liters. Now, here's where I'm sneaky. I can go V1 is 3 liters. V2 is how many liters? If T1 is 50 degrees Celsius and T2 is 100 degrees Celsius. And again, I'm assuming there's not a phase change here. So some are going to say, oh, it's going to be 6 liters. And if you say that, you would be wrong, because the absolute temperature scale is what we have to deal with here, not the Celsius temperature scale where we have negative numbers possible. So you have to convert to Kelvin. So 50 Celsius, 50 into 73 is 323 Kelvin. And T2 is 273 plus 100 is 373 Kelvin. So V2 is V1, 3 times 373 over 323. So 3 times 373 divided by 323, 3.46 liters. So the volume does go up. It doesn't double, but it does go up. Okay? So that is an example of Charles's law. So we looked at Boyle's law, Charles' law, and let me just go to File, New. Okay. Oh, that's not a good size, is it? Let's resize the canvas. There's not many letters I could write in there, is there? So there, that's better. Okay. Okay. So the next law is called Avogadro's law, not avocado, but Avogadro's law, where the volume is proportional to the number of moles. Is that it? Let me check here. Early 19th century, Amadeo Avogadro found that the volume of a gas also changes when the amount of gas changes. The more gas you have in a box, if pressure is going to stay constant, temperature stays constant, then the box has to expand. If we double the amount of any gas while keeping the temperature and pressure fixed, the gas volume doubles. In other words, gas volume is proportional to the amount of gas. So that's called Avogadro's law. So if they're directly proportional, that means V1 over N1 equals V2 over N2. So if I have a volume of gas of 5 liters and I have 4 moles in there, I could have given it to maybe in grams, and then you got to convert to moles. Then if the volume doubled, then my N2 would have to be V2 over V1 times N1, so 10 over 5 is 2 times 4 is 8. 8 moles. You double the volume, you double the number of moles. Okay, so that's another one. Another law that is, the book doesn't mention so much, but explicitly is Amantan's law, which is pressure is proportional to temperature. So the greater the temperature, the greater the pressure. And this is again at fixed volume and number of moles. Now this is important if you're driving, because you're driving for a long time in a hot climate. Well, the friction on the tire is going to make it hotter still, and there's going to be greater pressure exerted against the walls of the tires. It's why when you're measuring tire pressure, you aren't really supposed to be doing it right after you drive, because of the friction causing the temperature increase, which causes a pressure increase. So you should wait till it cools off. So that's Amantan's law. We could write it, and of course temperature has to be in Kelvin. This is all related. So P1 over T1 is P2 over T2. So if I had, let's say, 4 atmospheres at 25 degrees Celsius, which is 298 Kelvin, and then I went up by 10 degrees Celsius, so I'm now at 308 Kelvin. I could get P2, so it would be 4 times 308 over 298. 4 times 308 divided by 298, which is 4.13 atmospheres. Okay. Now, I can put all these equations together. And make what's called the combined gas law. I'm doing this in a bit of a different order than the book. And the combined gas law, I can put all these together. P1 V1 over N1 T1 is P2 V2 over N2 T2. So this summarizes all the laws. Now, some people call that the general gas law. Some call it the combined gas law. Let me see how our book does it, because some books don't call it anything. How about that? Our book's not going to call it anything. So you don't have to give it any name. Just know that this equation here is going to allow us to look at changes in pressure, volume, amount in moles, and temperature when we change at least one of the properties. Before we get to that, we have what's called the ideal gas equation. And depending how far you got in the grade 11 chem, you may or may not have seen it before. The product of pressure and volume equals the product of the number of moles times the universal gas constant, capital R, times the temperature, where the temperature, of course, has to be in Kelvin. So PV equals nRT. Gas is ideal if it obeys the ideal gas law. That is the definition. It sounds a little silly, but that is the definition for ideal gas law. And let's see. Okay, someone's barking at me. But I'll just let them keep barking. I think they're now going to drive away. That's my dogs every now and then give some input onto various equations. So R typically is just called R is known as the gas constant. Okay. So let's go back to the textbook and see what's happening there. So yeah, you can prove the gas law by this. You know that volume is proportional to the number of moles. That's Avogadro's law. And the temperature, that's Charles's law. So it's proportional to both. So it's proportional to the product of both. And it's inversely proportional to the pressure. So I replace that with a proportionality constant called R. And V equals RNT over P. Or PV then equals nRT. Okay. So solving quantitative problems with gases at moderate temperatures and pressures requires only one equation, the ideal gas equation. At extreme temperatures and pressures, you have to do deviations from the ideal gas equation. But in most of the ones we'll look at, it'll be fine. Temperature in kelvins. Now, there's different units you can use for R. If you're going to express pressure in kilopascals, volumes in liters, and ends in moles, N is in moles, then R is 8.314 liters, kilopascals, moles per Kelvin. Okay. If instead you're going to use bar, volume in liters, and N in moles, R is 0.08314. So C shifts over by 100. 1, 2. Yeah. 0.08314 liters bar per mole per Kelvin. If we use SI units for both pressure and volume, then it's 8.314 cubic meters, pascals, moles per Kelvin. You'd be given all these on a test, all these values of R. You don't have to memorize them. So the choice of which R value to use depends on the units for pressure and volume. Okay, so let's try a few of these examples and see how that all works. So let's say we have a 10 cubic meter steel storage tank, contains 8.85 kilograms of methane. I know right away I got to convert that to grams and then to moles. Temperature 25 Celsius, I know right away I got to convert that to Kelvin. You don't really need to put the 0.15 very often. I'm not going to bother, just add 273. What's the pressure? So P is nRT over V. PV equals nRT, so P is nRT over V. And so the number of moles is 8.85 times 1,000 divided by 6. So 551.7 moles. R is 8.314 cubic meters, pascals, moles per mole per Kelvin, temperature 298.15. And I can keep the volume in cubic meters. And I get a pressure of 1.37 by 10 to the 5 pascals. Verify that the units cancel out. Well, let's see. Moles and moles to minus 1 cancel out. Per Kelvin and Kelvin cancel out. Cubic meters cancel out. So I'm left with units of pascals. Okay. Determine the new pressure if the tank is stored in a hot location where the temperature reaches 42. I'll let you try that yourself. All you'll do is you'll change the 298.15 to whatever 42 plus 273 is. Okay. And if you want more practice, problem 2.12. Okay, let's try example 2.3. This is on page 65. And pressure gauge, that's how it's pronounced, on a tank of molecular oxygen gas. So that's O2 gas. 32 grams per mole is the molar mass. I think I'm going to need that. There's the pressure, 5.67 bar. Volume, 75 liters. Temperature, 27.6. I'm going to have to add, oh, they do decide to add 273.15. Fine. 300.8 Kelvin. How many grams of molecular oxygen are in the tank? So first I'll get the moles, and then I'll multiply my molar mass to get the grams. So the moles N is PV over RT. The pressure is 5.67, and hold it. What's this here? I get these important messages every now and then. Huh, really? Okay. That's a funny thing. I'll share that with you later. Okay. Pressure. Why am I going to kilopascals from bar? Oh, because I use kilopascals here. So 5.67 bar is 567 kilopascals. So I converted bars to kilopascals. Keep in liters, and then the liters will cancel, the kilopascals will cancel, the kelvins will cancel, and the per mole goes upstairs to become moles. So I get 17 moles. Okay, so you got to do the right conversions of units to have things cancel out. So it's always a smart idea to put the units in the intermediate step. Kids say, oh, that's long and boring, but you're not going to have to do it that much, and it makes sure that you aren't going to make a silly unit mistake. So 17 times 32 gives 544 grams of oxygen. Okay. let's try this practice exercise together. For fun here, 1.23 gram sample of neon in 1.5 liter glass bulb has a pressure of 745 torr. What is the temperature in the lab? So T equals nRT, PV equals nRT. No, okay, so I was trying to show off there. That's no good. PV equals nRT. So T is PV over NR. The pressure is 745 torr, or 745 millimeters of mercury. Now let's convert the torrs to kilopascals. Okay, so I'm going to go to that page. 1 torr is 133.3 pascals. So 1 torr is 133.3 pascals. So I multiply by 745 torr, 133.3 pascals in 1 torr, and let's go to kilopascals. 1 kilopascals is 1,000 pascals. So 745 times 133.3 divided by 1,000 is 99.31 kilopascals. So 99.31 kilopascals times a volume of 1.5 times N. N is number of moles. So it's 1.23 grams divided by the molar mass of neon. Oh, I need my friend the periodic table here, don't I? Neon is 20.18. 20.18 grams per mole. 20.18 grams per mole. So 1.23 divided by 20.18, 0.061 moles. Okay. So now what R should I use? I got units liters, kilopascals, moles, and Kelvin. So I'm going to use the 8.314. Liters, kilopascals per mole per Kelvin. So everything cancels out except the Kelvin, which is what I want. So 99.31 times 1.5 divided by 0.061 times 8.314. 293.73 Kelvin. Now sometimes I'll be tricky and I'll say, what is that in Celsius? So you've got to subtract. So you get 20.7 degrees Celsius. So this is practice exercise 2-3. Let's see if we did that one correct. Looking at the back here. Practice exercise 2.3. 21 degrees Celsius. What did I say? Yeah, they're rounding. Yeah, we're good. 20.7. 21. Hooray! Okay. So, a useful quantity is the molar volume of a gas. Molar volume, old days, and some people still write molar volume has a V with a bar over it. It's how much volume is occupied by 1 mole. Volume of 1 mole of a gas and must be expressed at some specified pressure and temperature. The molar volume can be easily calculated using the ideal gas equation. And for example, if we want to get the molar volume at some common set of units, let's say 25 degrees Celsius and 100 kilopascal, which is roughly close to common room temperature. So PV equals nRT, so V over N is RT over P. So 8.314 liters kilopascal per mole per Kelvin times 298.15 Kelvin divided by 100 kilopascals. So you get 24.79 liters per mole. That's not STP. Some of you may recall STP, a little aside on STP, standard temperature and pressure. That's 0 degrees Celsius and 1 atmosphere. and the molar volume would be 22.4 liters per mole. Okay, that you may have used before, STP, and it still is a useful concept. And here we have a concept. If you're doing lots of stuff at 25 degrees Celsius and 100 kilopascal, the molar volume, 1 mole, will occupy 24.79 liters. Okay, so let's see an example of that. Here's a cement factory, produces large volumes of carbon dioxide gas by the reaction of calcium carbonate, goes to calcium oxide plus carbon dioxide gas. If you get 10 metric tons of calcium carbonate per hour, what volume of carbon dioxide is produced? Okay, so per hour, 10 metric tons. A metric ton is 1,000 kilograms, so 10 times 1,000. So 10,000 kilograms, so kilograms 1,000 grams, so 10,000 times 1,000 is how many grams of calcium carbonate, and that's going to be the same as the, well, no, now I've got to convert to moles, so I get the molar mass of calcium carbonate from the periodic table, 100.1. So 9.99 by 10 to the 4 moles, which is going to be the same as the moles of carbon dioxide generated, multiplied by 24.79. And you get 2.48 by 10 to the 6 liters per hour. Okay, and that's important for environment and designing, things like that. And you can try the practice exercise on your own for 2.4. Okay, so what if we do variations? We can change any of the variables and what will happen. And so if we, well, what we're really doing here, and I'll do these quickly since I did some before, but sample of helium gas is held at constant temperature, and is it a sample? We aren't going to take some helium out or put some in. We're just going to slide a piston, exerts a pressure of 1.5 bar. If you got a new pressure of 2.1, what's the new volume? So I mean, the book uses I's and F's. I used 1's and 2's. So V2 is P1 V1 over P2 and 0.57 liters. So you can go through that. I did example of that before. Good strategy for organizing gas calculations is to determine which variables do not change and rearrange the gas equation to group them all on the right. Yeah, okay, so you're isolating for the thing that is going to change on the left. Here I'm looking, this one I'll do because it has, this is either called the combined gas law or the general gas law, and I think some books just don't talk about anything. So we got an example 2.6, a sample of carbon dioxide. I mean, everyone talks about this, but they don't all give these specific names. A sample of carbon dioxide in a 10-liter cylinder at 25 degrees Celsius, 1 bar, is compressed and then heated. The final temperature and volume are 55 degrees Celsius and 5 liters. Compute the final pressure. So here we have a nice, some of you like little drawings here. So I got 10 liters to start with, an initial temperature of 298 Kelvin, right? We might as well take care of that right away. An initial pressure of 1 bar. Now we're going to compress it, so the volume will go down, but we're going to heat it, so the volume will go up. So they're having a battle here. The question is, what's more important? And it depends on the numbers. So our final volume is 5 liters. That's a compression. We have increased the temperature, so our final temperature is 328 Kelvin. So we want to calculate P final. So P final is P initial, V initial, T final over T initial, V final. Okay. Some of you say, what about the N? Well, I'm not taking in or removing any carbon dioxide, so I can just not include the N. Or N2 equals N1, N final equals N initial, so it cancels out. So P final, punch it in, you get 2.2 bar. Okay. The pressure is increased, which is what we expect because compression increases the pressure, and a temperature increases also increases the pressure. Okay, so they weren't, I think I said they were fighting. They aren't fighting. Both of these effects cause an increase in pressure. Due to Boyle's law, we get an increase in pressure because the volume is decreased, and due to Amantan's law, we get an increase in pressure because the heat increases. So both those factors cause an increase in pressure to 2.2 bar, so a bit more than double what the pressure was initially. Okay, and then you can try the practice exercise on your own. Example 2.7, I never liked that example, so I'm going to leave that one out. Let's try 2.2.3 for fun here. This is a section exercise question. A 1.5 liter gas bulb, so V1 is 1.54 liters, contains oxygen gas at 21 degrees Celsius, so that's 273 plus 21. 273 plus 21, 294 Kelvin, and a pressure of 758 torr. Do I have to change that? Maybe not. Let me just write it, 758 torr. The air conditioning in the laboratory breaks down. That's great. The temperature rises to 31. So T2 is, it was 21, 294, so now it's 304, right? And what pressure does the gauge show now? Now the bulb, I'm going to assume that it's 1.54 liter. They aren't telling me that it is being able to expand or not, so I'll have to assume, to answer this question, that V2 is the same as V1. So I just got to get the pressure. So P2 is P1 T2 over T1. So 758 times 304 divided by 294, 783.8. Let's see if we're right here. And that's torr. So on the section exercises 2.2.3. Remember, the section exercises are at the end of the chapter. 784 torr. What do you say? 783.8. That's good enough. Okay. So practice some of those, and that's good to end it for this first lecture. And in our next lecture, we're going to look at gas mixtures and Dalton's law of partial pressures. Have fun.